Okay, so hi everybody. Welcome to our weekly seminar at the Institute of Astrophysics in Crete. Today we have the pleasure to have with us Dr. Vishal Gajjar. So briefly about Dr. Gajjar, he has obtained his PhD in physics from the National Center for Radio Astrophysics in Pune in India. And he's currently a staff astronomer at the SETI Institute and a visiting researcher at the University of California in Berkeley. His research focuses on developing novel algorithms to search for evidences of technologically advanced extraterrestrial life, studying fast radio bursts, and understanding radio emission mechanism of neutron stars. So thank you very much for being with us. The floor is yours, Michelle.
Thank you, Carolina, and thank you, Avinash, for inviting me to give this seminar. I'm very excited to speak to you all about our this piece of work. So as Carolina mentioned, I work on various different topics, and one of them that's kind of quite close to my heart is searching for evidence of technologically advanced life. And that is what I'm going to talk to you about today. What are the new advances that's happened in this area? What new effort that we have kind of enabled to really answer this question that are we alone in the universe? So in general, I think my talk will be divided into these 4 different segments. Like I'll first try and justify why we should search for evidence of life in the universe. What are different ways by which one can find? What are the possible challenges that we currently face in order to do our research, and what progress we have made so far. So let's just start with an obvious question, like which I don't really need to kind of do justify to this audience, because I'm sure all of you probably have some astronomy background, so you are all familiar with the possibility of Earth-like planet or possibility of life in the on other sort of stellar system is highly likely, given the number of stars we have, number of exoplanets that we have discovered so far. So like just the exoplanet itself suggests that Earth is not so unique. Like we used to believe a few decades ago that Earth is sort of in a very unique position, and like Earth is sort of one of the rarest planets. But it seems that's not the case. We found hundreds and thousands of basically other exoplanets, and many of them are inside what we call the habitable zone as well. So it's unlikely that Earth is such in a unique condition. So other places should have life on it as well. So given that there's other life is there, this is what we can assume right now, right? Like in earlier days, what we used to think is that sky is full of stars, but now we can think that almost every star, when we look at the night sky, most likely will have planets going around them. The other piece of sort of evidence, or other piece of sort of encouragement we have in terms of life is progress we made in astrobiology. So over the last few years, we have also found life at extreme environments where we do not expect life to exist. We have found these extremophiles to exist at such a harsh environment where we never expect any kind of life to ever survive, but we do find it there. This all seems to suggest that even our concept of habitability needs to be sort of broadened up. We are always kind of trained to think when we talk about life that planet needs to be at the exact distance, the condition needs to be perfect. Life may not need all that. It can survive harsh environment of space. It can also basically thrive in an extreme condition. So it is possible that we should expand the parameter space. And this gives us more hope that there will be more possible likely places for life to exist and evolve. Hence, there is a possibility of extraterrestrial life as well. So if we have possibility of life, the natural progression of life is evolution. We have seen a number of sort of mass extinction events in our past, but we overcame all that and we survived and thrived and became more and more intelligent, and the final product is us human. So in summary, like life finds a way. Like once you have life started on a place, it is going to evolve, it is going to survive, it's going to kind of adapt to its environment and evolve, and eventually it is going to create more sort of advanced life. So the question is, And so these kind of life, I think it should be possible to search within our lifetime now. So there is already an effort going on in JWST in trying to measure the transmission spectroscopy of exoplanet in order to detect what we call biosignatures. So these are like telltale signs of biomolecules, so life that might exist on these exoplanets. So unfortunately, with the current sensitivity, this may not be possible to do for a whole number of systems, but at least within a few light years, a few tens of light years, we should have some idea about the presence of biosignature on some of these systems that we are going to target with JWST. So it's a progress in the right direction. But what about intelligent life? So we will definitely be able to find, maybe we'll some evidence of biosignature. But what about technologically advanced? What about more intelligent life? Is there a way for us to find intelligent life? So that's the question. So I hope that should have been able to justify that the possibilities of existence of intelligent life exist is non-zero. So there has to be other life. Now the question is, what are the different ways by which one can find technologically advanced life? So similar to biosignature in our area, we call that technosignature. So biosignature suggests you presence of biology, technosignature suggests you presence of technology. So what are different technologically sort of technosignature that one can look for with our current existing technology that is already there? So the first thing this has been proposed in 1959, so long ago. People have already suggested that if you look at a radio spectrum, most of the natural occurring signals, most of the natural occurring sources produce broadband signal. And even if they produce spectral line, they are still several thousand hertz wide. So if you detect a signal that is only 1 hertz or like a few hertz wide, that means that is engineered signal. That signal is produced by technologically advanced life, because we do that quite often. We produce carrier waves when we make transmission. None of the natural sources or natural phenomena that we know of can produce signal that is extremely narrow in frequency. So if you do detect it, that's a very good sign that it is basically been produced by technologically advanced process. So that's a good technosignature. There are other technosignature as well. People are trying to search. For example, a few years ago, they discovered this exoplanet transition light curve, and they detected that there are periodic dips in them, and each dip actually had a different intensity of obscuring their parent star, which is quite unusual, because if you expect a planet of a more or less same size every time it transit, it should be periodic, and also like every time it transit the star, you should also see the same amount of dip. But people have basically seen a different intensity of dip, which might suggest some kind of like an artificial structure around the star. This has been speculated. There are papers on it. Eventually, it was ruled out, but this was a good way by which we can also search for extremely higher technologically advanced life. People have also suggested other forms of sort of communication, or other forms of sort of like in optical domain. For example, Charlie Towne, who is also from Berkeley, who won a Nobel Prize for discovering the lasers. He himself, with Schwartz, wrote this paper in '61, where they speculated that nanosecond duration optical pulses could also serve as a way by which one can transmit information across large interstellar distances. So again, serving as a type of kind of a technosignature. There are other forms of technosignature as well. For example, we proposed this a few years ago, where you can mimic a signal that is coming from astrophysical source, but modify it in a way that basically suggests artificiality. Like, for example, what I'm showing you here, it is an example of what a typical pulsar would look. So on the left-hand corner, what you see is the typical signal from a pulsar, if you're able to see my cursor. But all the other 3 plots are what we call artificially corrected or artificially sort of changed signal. So if you have a signal like that, we don't know of any natural processes that can give rise to these. So if we do detect a signal which kind of show these characteristics that are highly indicative of technologically advanced life. There is another sort of work that we did last year with one of my students, where we're actually searching for narrowband but pulsating signal. So again, this is something that in nature we have never really seen, something that is pulsating but also confined to a very, very small frequency range. So if you see a narrowband signal, but pulsating narrowband signal, again, this could be an indicative of technosignature. So there are different types of technosignature that we currently search for. Now, idea is that do we have sensitivity to detect this across large interstellar distances? And answer is yes, we definitely do. For example, this is Arecibo. Most of you are familiar with that. Unfortunately, it's no longer active. But the kind of transmission that Arecibo is able to produce, it's so bright that you can in fact able to detect them all the way to the other end of the galaxy. There are also quite powerful planetary radar signals that we produce. So this is one of the DSN dishes from NASA. We broadcast this high intensity radar signal to detect asteroid in our solar system. So these radio waves also penetrate and they travel or could travel basically all the way to the other end of the galaxy. So you should be able to detect them with a similar class telescope like Arecibo, even if you're sitting in the other part of the galaxy. There are also hundreds of other transmitters that we have, like this is the super tower in the Bay Area where we are located. It's just a sort of early warning system, and you have lots of mobile transmission. That's all part of it. But the purpose, there are thousands of these all across the world. And if you look at the collective power of all of it, they are basically detectable across interstellar distances. So in fact, one of the students working with us, he did this calculation. So he basically calculated, he's one of the PhD students going to University of Manchester. What he did is that he basically looked at all the different mobile phone towers across the world and looked at its collective output power. And what he measured is that, let's say there is a intelligent life sitting in this particular star named HD, and it is looking towards Earth, what kind of power level it's going to see from all the mobile phones that we have on the ground. And he measured that that's actually in gigavolts. So this is a good number to remember. That is 10 to the power 9 volts. That's a huge amount of power that collectively all our mobile phone towers are actually transmitting. And then it's detectable up to like a few hundred, at least a few tens of light years. So we are detectable for sure. How likely it is that we were able to find life in our sort of vicinity. Now that's obviously the question for more theory side of thinking. I mean, because we really don't have a lot of understanding about some of these terms of Drake equation. I'm sure many of you are familiar with the Drake equation. It's just a theoretical framework of putting our sort of all the different possibilities for life, combining together and multiplying the probabilities of different times. For example, like what is the fraction of star will have planets? What fraction of those planets will have sort of sustainable environment? How many of them will have life on it? So forth. Basically, combining all these terms. So there are a few things we know about, but a few things we have absolutely no idea. Like, for example, we may know the star formation rate at different part of the galaxy. We probably also know the fraction of stars with planets based on our current estimate. But we certainly don't have a really good estimate of number of the Earth-like planet or fraction of habitable planets where life could arise. And certainly have actually no idea about intelligent life and like life that can create technology. So there are a lot of unknowns. So one can take different approaches. You can either take a very pessimistic approach and assume the chances is less than 1% in most cases, and then you end up having maybe one intelligent life per 100 galaxy. Or you could be extremely optimistic and you could perhaps try and take what is currently known from our research, and we say that, okay, there is a highly likelihood of finding other intelligent, highly likelihood of existence of an intelligent life, and then this number is quite large. That means that it's one intelligent life per million star. So we don't know what the real number is. And I think this is a really good quote from Carl Sagan, that the only significant test of the existence of extraterrestrial intelligence is an experimental one. So unless and until we do an experiment, we test this hypothesis, we really don't know. So whether it's and the answer could be somewhere in the middle. We don't know, right? It may not be totally pessimistic. It may not be completely optimistic. It may be somewhere in the middle. So until and unless we carry out observations and tests, we would not know. So with that goal in mind, Breakthrough Initiative was launched now almost like 10 years ago in 2015 at the Royal Society, London, with Stephen Hawking, who was one of our early advisors and who was one of our early leads as well. And our ultimate goal, and currently, as I mentioned, I also mentioned briefly earlier that we started this at Berkeley, but recently we also had our international headquarters moved to Oxford to be more, have a little bit more proximity to SKA and be more international. Like earlier, it was more US-centric effort, but now we want to make it more global. So we have our headquarters at Oxford as well. So what are we doing exactly with the Breakthrough program? So we have several sort of targets in mind. So if you take a very sort of optimistic approach, then you're likely to find life in our own solar neighborhood. So we are looking at our nearest star. We're looking at the nearest million sample. I'll not go into a lot of details about the star selection, but you can kind of have a look at these texts. We made some criteria through which we selected our star sample, and we are in the process of surveying them. If you be totally pessimistic, then maybe the life is sort of very rare, and that means that we need to look at extragalactic sources as well. So we need to look at nearby galaxies. So we are looking at 100 nearby galaxies in our sample. We are also looking at our galactic center because at that particular line of sight, as you can see in the plot here, so we are here, and if you look towards the galactic center, that cone gives you the largest number of stars that you can get compared to any other direction. So you have a highly likelihood of finding life, highly likelihood of encountering life if you look towards that direction. So we do also have a good amount of survey conducted towards the galactic center. So just to recap about this idea about intelligent life. So this is how this summarizes our entire process. So we are in this Milky Way galaxy, and we are expecting that the galaxy is filled with a lot of sort of life around it, which are broadcasting this radio signal traveling across the Milky Way. And to be more focused, let's just look at one of the subsystem where you have life on it. This is an exoplanet which eventually developed intelligent life. We developed technology, and then it started sort of transmitting or started leaking radio signal, like what we do right now. We have this mobile phone tower, aircraft radar, planetary radar, everything sort of broadcasts out, right? So we created this bubble of radio emission, and due to some reason, we stopped broadcasting. Maybe life perished and no longer exists. But the radio bubble kept on expanding. So we here sitting on Earth, we are also kind of broadcasting. When we encounter the radio wave passing through us, what we can do is that we can use powerful radio telescope to detect it. So we use this telescope called Green Bend Telescope in West Virginia here in the US. And the second telescope we use is the Parkes Telescope in Australia. But these are not the only telescopes that we use. We use a number of other facilities across the world, primarily to basically conduct these searches. So GBT and Park, as I mentioned, are our sort of main facility where we conduct a large amount of our searches, but we also do 24/7 observation with Meerkat, but we operate commensally. So we piggyback on other observation because for us, we really have no idea where potential life could, we can create a list of targets, but we should try and basically look at all different parts of the sky. So Meerkat allows us to do that because Meerkat is an interferometer. So we can do our own beamforming. So we have a quite, maybe I'll have a chance to talk more about it. So we do our own beamforming and we do our own sort of observation with Meerkat. Not only radio, we also search for technosignature in optical. So we have this automated planet finder here in Lick Observatory in California. We also have a Veritas telescope, which is actually a high energy telescope. there are other telescopes that kind of spread across the world where we also conduct technosignature searches. And talking about the frequency coverage, so we go from all the way from like 30 megahertz to all the way high to like Veritas, where we actually look at 600 nanometers. So this is a huge range of electromagnetic spectrum that we search across various different observing facilities. And just to give an idea, I'm sure all of you are familiar with radio telescope, but this is a Green Bank telescope, which is enormous in size, 100 meters in diameter. It's equal to 2 football field. The best thing about it that it gives you a frequency coverage from 1 to 93 gigahertz. That's just covering the entire radio window, because as you know, our atmosphere doesn't allow all the entire electromagnetic spectrum, which is a good thing because we don't want X-rays and gamma rays to penetrate our atmosphere, but we only have accessibility from 1 to 100 gigahertz. Beyond 100 gigahertz, the atmosphere start absorbing electromagnetic waves. So GBT sort of ideally placed to cover the entire range, which is great, and we use it quite a lot. All right, so I hope I'll manage to sort of give you a brief overview of all the different facilities and all the different telescopes that are currently working with us in order to search for technosignatures. So that probably hopefully answers what are we doing. So what are the challenges? Like, okay, we do have a lot of facilities, we do have a lot of observing time across these many observing facilities. What are the main challenges? So I like to divide the challenges in two different parts. Like one is very obvious, right? We have absolutely no idea what we should be looking for. And the second thing is that when we try to look for engineered signal that can be produced by technology, we always have to work around interference, like interference that is produced by our own technology. Like, how do we distinguish something that is produced by extraterrestrial intelligence versus something that is produced by our own technology? So that's a bigger challenge for us, that we can think about various different ways by which we can eliminate. I'll kind of give you a brief idea about different techniques that we use in order to eliminate sources of interference. Let me give you an example of the first thing. What are the different kinds of signals we try to search, and what are the challenges, right? So the first challenge, obviously, as I mentioned earlier, that we try to search for different kind of radio signal. Like I already mentioned about the narrowband signal, broadband signal. We also try and search for signals which have modulations in them. Any kind of modulation which is coming from one particular part of the sky is an indication that it is produced by engineered signal. But the problem is that this is a kind of every radio telescope, unfortunately, is surrounded by our own technology. This is an example of Parkes telescope. I don't think so Parkes people like us using this graphic, but this is definitely not representative of Parkes. This is typically true for almost every radio telescope, that they have to deal with interference. Even if the GBT, which is located in a what we call radio-free region, so we have isolated. So actually, the government has isolated a part of that region that nobody's allowed to use any radio technology. You're not allowed to have like Wi-Fi routers if you're living in that particular zone. But still, we get a lot of interferences because we are using radio for almost everything. We use there's satellite that are directly communicating with our cars, with satellite radios. We have Wi-Fi routers. We have a number of sort of mobile phone transmitter all around us. So everything interferes with us. The signal kind of seeps in. The biggest challenge is obviously satellite. Like this is just an overview of what satellites are there in the sky. And you can see there are hundreds of satellites. There are thousands of satellites, in fact, right? At any point when we are looking, there are satellites that are passing and zooming in our field of view. So we do get a lot of signal from satellites. So how do we basically manage that? That's a huge challenge. So one of the ways by which we try and eliminate sources of interference is by using this technique called on and off switching. So what we do, for example, with telescope like Green Bank, is that we stare the telescope towards one particular star for 5 minutes, and we try and look for possible signals in that direction. So, for example, if you see what you are seeing here, the y-axis is time, which is increasing from top to bottom, and the x-axis is frequency. And what you're seeing in the yellow color is an example of a narrowband signal that is there for a brief amount of time. So when we look away, that signal should disappear if it is truly coming from that star. So we do this 3 times on and off technique. And if the signal persistently only exists towards the direction of the star, that is an indication that it is probably coming from a star. There is still not final confirmation. We have to do a lot of checks as well. But this is a good starting point. Like, this is an interesting source that is showing you a signal only when you look towards the star, and it disappears when you look away. The other technique is multi-beam approach. So GBT has multi-beam at other higher frequency, like Parkes telescope had this multi-beam array. So we did quite a lot of survey with a multi-beam. So multi-beam allows you to look at a large number of pointings in the sky. So this is a Parkes multi-beam telescope, which can actually look at 13 different parts of the sky. It is no longer sort of operational. They replace it with the ultra wideband receiver, but they are also in the process of having another multi-beam receiver. But we use the FAST telescope, which has the 19 beam configuration, so it can look at 19 different parts of the sky. And this is another way by which you can look at multiple beams at the same time, so you don't have to do on and off, and you can try and fix one of the beam on a target of your basically of your source, and we try and see if the signal only exists in that beam and not in the other beam. And that way you can eliminate anything that is produced from local interferences. The other trick we do is we try and use facilities that are widely separated. For example, these are telescopes in Europe, in Ireland and Sweden. And these 2 telescopes are at least more than 1,000 kilometers apart from each other. So we try and observe from both these facilities. Obviously very bad representation. It doesn't do it like that, but obviously you get the idea that when it tries to look at a same source, what we try and do is that any source of interference are mostly isolated. Let's say you have a transmission tower close to one of the antenna, then it will get picked up by that, but not by the other. And that way you can eliminate interferences like that. But the best thing is also using interferometer. So we try and use this interferometer called Meerkat, as I mentioned earlier, which actually can look at multiple parts, multiple sources at the same time. Because typical radio antennas in element like Meerkat, individual elements are quite small, so their field of view is quite big. In fact, several degrees. So what it can do is that it can look at a large part of the sky. And then what we do is that we digitally beamform in that particular part of the sky toward the sources of our own interest. So as I mentioned earlier, with Meerkat, we always do a piggyback observation. So anytime there are observations happening for other science cases, for example, if somebody is observing a pulsar, in that same field of view, you may have a lot of other targets that are potential to search for life. And we do try and form beams toward these targets, and we search for signals of our own interest. And again, this is multiple beams, so you can do the same trick. You can compare the signal from all of these beams and try and eliminate sources of interference that are probably local and will appear in all the beams. Similar thing we are trying with the GMRT as well. And in fact, Avinash, I think, who is currently among you, he initially worked with me on this project of building a pipeline with GMRT, which sort of like the first step in that direction. And we are currently making more progress in deploying this. And we are in talks of doing similar commensal observation like we are doing with Meerkat with the new system that they are currently updating. So I think this probably covers the part about different observational technique, but what can we do once we get the data? Like, are there ways by which you can, even if you could try and do the smart things about observationally, it will still sits into data. So there's so much data, and we don't really have a lot of time to really go on everything. We generate a terabytes of data per day. So this is a huge amount of data that we generate across all our observing facilities. We really don't have time to see through all of it. And that's why we use AI in order to isolate things that are sort of more unknown, something that we kind of identify as an interference. So we train a lot of ML model. And this is an example of, for example, this is an example of an FRV, but the idea is still the same, that we can train a CNN-based classifier to search for things that are interesting to us, and then we let it free on all our data. So when you talk about AI, there are two different kinds of things that we can search for. Like one is finding a known type signal. Like obviously, in case of known, is quote unquote, because we don't know what kind of signal ETI might be broadcasting, but we can create hypotheses, like similar to like narrowband signal. So we call the narrowband signal a known signal because that's the signal that we have already thought about and we have designed tools to search for them. So we call them a known signal. And if we already know that what kind of signal we want to search, you can design your signal classifier to search for that. And I'm sure all of you are familiar with the convolution neural network that in CNN, what you can do is that you can create examples of many such signals. You can create thousands and thousands of sort of example of signal, and then you can train your classifier in a way that it will give you a probability of anything that it sees, how likely it is to match with one of the things that it has sort of trained before. And this is also kind of similar to like self-driving cars and other things that they have currently already been deployed. So when you talk about known kind of signal, like these are like some examples of like known kind of signal that we can create a hypothesis for, and we can try and design a convolution neural network. So we do have CNN for these, at least these three category of signal. And I like to also briefly mention about the modulation pattern because I didn't get time to go in much detail about it. So we also have, there are 24 different types of modulation that we currently use for communication. So what you can do is that you can train a CNN classifier to identify any kind of sort of known modulation type. But the beauty of this is that we can also train it in a way that if it sees the modulation that it cannot isolate into any of the known category, it can always isolate as an unknown modulation category. And we tried this and it does work. So what you're seeing in the bottom plot here, this is what we call a t-SNE plot. This is just a sort of a two-dimensional representation of clusters in a hyperdimensional parameter space. And each color cluster is one type of modulation. But what's interesting is that even if our sort of model is trained to identify a known kind of modulation, it can still identify an unknown modulation into its own separate cluster. And this is a very clever way by which we can isolate things that we can't even imagine. We can't even think about a certain model because there is absolutely no way that ETI is using the same modulation trick as what we are using. This is very anthropocentric, right? So we have to design a tool which can also search for any kind of modulation that we can't even think about right now. But if it has some kind of energy fluctuation and repeatability, that is still a way by which you can isolate it. So we can use the same tool to isolate an unknown kind of signal as well. And that brings me to this thing like searching for completely unknown signal, like not even modulation, right? Modulation is still in some sense unknown thing because we do that quite a lot, but searching for complete unknown anomalies. So how do we do that? So for that, we use this technique called LSTM, long short-term memory. I mean, this is also used for identifying language models as well. And it's quite frequently used in LLM as well. So what it does is that if you feed in hundreds and thousands of hours of your observation, you can make predictions of what is expected to come after every event. So you can make predictions similar to like language, right? Like in language, you know how a sentence is formed and like what word is more likely to occur after a certain word. Similar thing can be done for observation. This is still work in progress. We have not completely deployed this. But the idea is that if you have observations, you feed a lot of your thousands of, we tested this and it does work. That if you feed thousands of observations, you can make predictions on your observation and you can make prediction that, okay, how likely it is that you will see this as your next observation. And if it matches, that's great. That's not an anomaly. But if it doesn't match, that's an anomaly. So if anytime you try and see things that you do not expect to find, that's an anomaly. So this is a completely different way of searching for signal that we absolutely have no idea about. If it is any kind of radio signal, it should be able to pick it up just on the basis of anomaly detection. Maybe this is still not enough. Like we try and all of this trick, the interference is always going to seep in, and we will always have to deal with it. So one of the ways with which Breakthrough Listen is also thinking about is going to the far side of the moon, because obviously Earth environment is highly polluted with interferences. There is no way to escape, for example, satellites. But one place which is sort of still isolated is on the far side of the moon. So Breakthrough Listen program is also initiating a design study. We are not really planning to deploy a telescope yet. This is just the very first design study. If, for example, you want to install an antenna on the far side of the moon, what technical challenges that we have to deal with? And this is already in work in progress. In fact, I think there will be some prototype, not by us, but we are not the only people who are thinking about it. A lot of people who are thinking about it, especially people who work in the epoch of reionization, because they want to look at extremely low frequency. Those frequencies are highly polluted. Also, the atmosphere creates a lot of problems for them. So for them, obvious places to go to the far side of the moon. And they are, I think there is a mission, I forgot the name, which is going to be launching next year to do a prototype experiment from the far side of the moon. So this is a great progress. And I think maybe in future, not in this decade, maybe in the next decade or so, we'll have sort of technologically sufficient advancement to have a telescope on the far side, which actually truly allows us to have a more RFI-free environment. So I think I currently already try and give you the idea of all the challenges that we face in finding these signals. Now, let me just finish the talk. I have, maybe I'll wrap it up in 5 minutes. What progress we made so far? Like, although we do deal with these challenges, what major progress that that we can kind of summarize. So there are a few things that we are quite excited about to share with you all. This is a paper that we published in Nature Astronomy a couple of years ago, where we actually detected a very kind of a similar signal that we expect to find from ETI. So this is what we call BLC1. And in case of BLC1, we basically detected a signal that lasted for several hours, and it was detected towards the direction of Proxima Centauri, so a nearest star. So we got very excited. When we first detected this signal, we all kind of put down everything what we were doing, and all of us focused on it. And eventually we were able to rule it out that it was still interference, but it gave us a really nice way by which you can eliminate false positive. It gave us a nice trick through which you can scrutinize any potential signal in future. And that's why we were able to publish this in Nature, that this paved the way for future discoveries. Like anytime in future, like if we ever make a detection like this, we will have a tool set up already to scrutinize that signal. So that's was an interesting case study. Second was that I mentioned earlier, we have deployed these ML-based algorithm, and this was the first application of searching a large amount of data for with ML, which was also published in Nature Astronomy. We also got quite excited about this particular signal. So this is towards Kepler 438, and this is from the FAST telescope. So let me explain what you are seeing in this plot. You are basically seeing 19 plots. And each plot is actually coming from one of the 19 beams. So you have so FAST telescope, which is a telescope in China, is equipped with 19 different beams, and it's looking at 19 different parts of the sky. And what we do is that we point the central beam toward the source of our interest, the source that we survey. And for each plot, what you're seeing, the y-axis is time, and the x-axis is frequency. So again, similar to what I showed you earlier, this is what we call a waterfall plot. So if you have a signal, a narrowband signal, it will only exist as sort of like a vertical line. And due to Doppler velocity, due to Earth motion, it will not be fixed, but it will be drifting, right? So what you're seeing in the central plot, you see the signal that is drifting. That's again a really good case, because this is exactly what we are searching for. Like if you see, that signal only exists in the central beam, which is where we actually place our source, that is Kepler 438, and it doesn't exist in any other beam. That's exactly what we're looking for. And this was a very unique case, and it was the only source that we found it. But unfortunately, when we looked at the polarization, we found that the signal was only present in one pole and not in the other. Now, it is highly unlikely that the polarization angle, and we did this observation for 30 minutes, it is unlikely that the polarization, even if the source is highly polarized, it doesn't necessarily need to kind of match the polarization angle of the antenna. So you are not expected to find high intensity of polarization only in one pole. So this was again ruled out as a sort of local interference by instrumentation in our pipeline. And eventually, like later on, we found similar looking signal toward other sources as well. So we were able to rule it out, but this was a really interesting case. All right, so let's kind of try and tackle this question about what, if I were to summarize the occurrence rate, and this is where we started, like this is what Carl Sagan scored is that the best test to existence of extraterrestrial is experimental one. So we did the experiments, like we are doing this experiment for a while now. So what limits we are able to place on the existence of intelligent life, right? So I try to summarize that with this one particular plot. So what you're seeing in this plot, the y-axis is what we call the transmitter rate per star, and the x-axis is the transmitter output power. So let's say you are a SETI astronomer and you did a survey of 1,000 stars and you did not find any signal. So what do? So you did not find any signal with a certain power level, right? Because you were sensitive of detecting certain power output signal. So what you're seeing in the x-axis is the output power. So let's say you, as I said, you did a survey of 1,000 stars. So the number of stars which has transmitter power more than you were sensitive to, it has to be lower than that. And the number of stars which will have that powerful transmitter has to be lower than that. So you basically, with your survey, place a limit that if ETI exists, it may exist in this particular direction. There is a bit of a sort of a periodicity or repeatability question as well, but I'm just ignoring it for a moment because signal may not be persistent all the time. It may be just coming and going. So you also have to be lucky. So there may be a third axis you can think about, but just to simplify, you can think of it in two ways, right? So you are able to eliminate. So what you're seeing here, it is at 10 to the power minus 3. So for 1,000 star, it has to be less than that, and it has to be lower power than what you were sensitive to. And if you compare all the surveys, so this is all the surveys historically, including what we've been doing with Breakthrough Listen, compared to what we were able to do. So if you basically take all the surveys, you take all the limits from all the different surveys, this is what we get. What you're seeing in the two vertical lines, let me explain that also. What you're seeing in the solid vertical line, that's the total transmission output power of Arecibo planetary radar. So remember, I mentioned this earlier, like Arecibo produces so powerful transmission that it is possible to detect it at all the way to the other end of the galaxy. So that is sitting at that limit. What you're seeing on the dotted line is the total transmission output power of Earth. So not Earth, but like some extremely advanced civilization, like what we divide the civilization into three categories, like Kardashev type 1, type 2, type 3. And type 1 civilization is a civilization which is able to kind of consume all the energy that is available on its surface. So an extremely advanced civilization, for example, will be able to transmit a power up to that level. So as you can see, we are sensitive, but we are still not extremely sensitive. What you want to go is somewhere in the left corner. So in principle, we eliminated this parameter space. We can say with surety that if ETI exists, it certainly doesn't exist in this region. The most likely place to find ETI in this region. So what we want to do is that we want to conduct more surveys and push the limit further down. And then we will likely go into the region where ETI might exist. Remember, I mentioned this earlier. Like, for example, if you want to talk about all the mobile phone tower transmission, that's in gigaport. So this axis that you currently see, it's in log scale. So it says that it starts from 10 to the power 10. So it's still higher. The axis itself, like the minimum in the X limit, is still higher than the total mobile phone transmission power. So far, our survey has not yet been sensitive to detect such an extremely low amount of energy even from a nearby, of a large number of systems. We may be able to do this for a couple of stellar systems that's nearby to us, but when you talk about a survey, we have not yet achieved, we have not really gone there. The future surveys will be able to allow us to push into this region. And I just like to kind of also compare this is with the historical sort of gravitational wave detection limit. So similarly, what you see on the left-hand plot is what people in the field of gravitational wave have been trying to do for the last 50 years. With different surveys, they've pushed the limit. And what you see on this gray region are the theoretical expectation of the different phenomena that can give rise to gravitational waves. And like different surveys, you can see different lines have pushed the limit further down and actually probe the region where you theoretically expect to find such sources. And eventually they detected. So we are, I like to think it in that terms that we are in that direction. Like we have not found ET yet, but with more surveys, we are pushing the limit. We are making our survey, we are eliminating a large amount of parameter space, and that way we are pushing the limit. And eventually hopefully we will definitely have answered this question that are we alone in the universe or not. So I'll just try to wrap up with this, that we don't know whether we're alone in the universe, but I think the prospect seems promising. So I thank you for your attention, and I'm happy to take some questions.
Thank you very much, Vishal. Very, very interesting. Very nice talk. So let me see if there is any question from the audience. You can unmute yourself or raise your hand if you have any question.
Hi, Vishal. This is Vaso Pavlidou. Thank you very much for the talk. That was extremely interesting. I have two questions. The first one is, can you say a few more things about searches in the optical? What exactly is being looked for there? You made a very brief mention.
Right. So with the Veritas telescope, we are looking for optical pulses. So I mentioned this, that Schwarz and Towns proposed this idea about nanosecond duration pulses. So with Veritas, we have a very fast read. Personally, I'm not an optical astronomer, so my sort of expertise will be limited. But what I understand is that we have a fast reader that basically looks at the time series and nanosecond time scale. And then it looks at pulsation that is happening in nanosecond. With APF, with Automated Planet Finder, it is actually a radial velocity experiment, right? So it looks at the spectral line. So we actually deployed a couple of more digital hardware to look at extremely narrow spectral lines. So similar idea as in radio, where we're looking for spectral lines, but extremely narrow spectral lines. Same way we are looking at spectral lines with the APF for extremely narrow optical lines. We do get optical lines from like sodium, from all the sort of light bulbs maybe around it, but most of it we can eliminate. So these are the two different ways, if I can briefly summarize, we are trying to do it in optical.
Thank you. And my second question is, clearly you have all of these very sophisticated software machine learning techniques looking for basically unknown types of signals, right? Something that you wouldn't other than what you expect, but things that you couldn't expect as well in terms of classification. Are you finding anything that is different in terms of astrophysics? So astrophysical serendipitously discovered astrophysical signals.
Yeah, that's a good question. We are hoping this will go both ways, that serendipitous discoveries, either through our effort, that what we are trying to do with the anomaly detection will help us also discover astrophysical. So far we have not, but what I can tell you is that we do have a couple of discoveries that we are very proud of. Like, for example, we discovered the fast radio burst at highest radio frequencies. This is again only due to our effort of deploying some of the cutting edge hardware. Like, for example, at the Green Bank Telescope, we have a hardware that can capture data across 64 compute node. We can write and retain raw voltages like baseband voltage because we have a huge amount of storage capacity. And this enabled us a discovery of FRB at high radio frequencies. Similarly, there are other astrophysical sources that we were able to do a detailed study because of our dedicated deployment of this sort of cutting edge hardware tool. So far, we have not discovered a new astrophysical phenomena, but I hope that with our effort, we will be probing in that region as well. And it also goes the other way, like typical astrophysical experiment, when, like, for example, they are conducting researches, it is possible for them to also find anomalies. Like, for example, the Voyager star that I mentioned, right? That was completely Voyager star was again an anomaly for exoplanet community, and we actually also have had a look at it. And technosignature was speculated, was also suggested as one of the arguments. So we did a detailed search and detailed understanding. Eventually, the community ruled it out. But again, this was a good case study. So to briefly answer, we have not yet discovered, but I hope that we are in that direction, because the anomaly detection would be a cool way by which you can discover new astrophysical phenomena as well. Yes.
Thank you very much.
Any other question? Yes, Grigory?
Hello. This talk. I have a question. I hope it is not provocative, in the sense that you try your best to eliminate all signatures, all interference patterns, and you have one signal that still you have tried all possible things, and still you cannot rule out. What is going on after that? What do you do?
Yeah, I mean, that's a good thought experiment. We came very close for this nature astronomy paper that I mentioned with the Proxima Cen discovery, where we tried all kind of different ways to eliminate it. We still couldn't eliminate. It took us a long time, several months, in fact, to rule it out. But you're correct. What happens that if something that goes beyond that? What happens if something that we cannot rule out? The obvious answer to us is that we will definitely write it up, and we go through a peer review process. If that's a sort of a standard approach for any scientist, like we try our best within our ability, and then we let others who are also expert in the area to be a judge of that, to allow us to also suggest other ways by which we can test it. And if by doing all the tests, what other peers have suggested, if we cannot rule it out, then it has to be sort of published. And that's probably going to be the most significant discovery humans have made.
I hope we have such publication.
Okay, I don't see. Well, I also have a quick question. So you told us that the total power from all cell phone tower is of the order of a gigawatt, and And instead, what you showed us is that in this parameter space diagram, we only, I mean, you're covering starting from 10 to the 10 watt, right? So we wouldn't detect the total power that we produce. But if we could reach that, we could have that sensitivity, would the signal from all the cell phone towers look like so narrow and with the characteristic you are searching for one of these signals?
So they will appear as one of the modulation because the mobile phone signals are modulated. And obviously, there will not be from one tower, and you have a number of different mobile phone towers. They all use a different frequency. So there is a bit of assumption that went into that. Ideally speaking, let's say that everything is transmitting at the same frequency, around the same frequency, and observing at the same frequency, then you have a detectability. In principle, signals being produced by different mobile phone towers are slightly different. They are not so much different. Like if you look at mostly at 900 megahertz or 1.6 gigahertz, these frequencies are heavily being used for mobile phones. So if you concentrate on these frequencies, one can detect Earth transmission as a leakage radiation at those frequencies. You may not be able to demodulate it because it will be sort of mix of everything together and just there won't be any coherence in there. You will not be able to detect any particular kind of modulation. But what you will be able to detect is that if you look at only that particular frequency, you will see an excess power compared to everything else. And that excess power will be coming only from one part of the sky or only one point. So that way you can eliminate that it's produced from technology and it's not produced by any kind of sort of natural processes or by interference. So we take the argument and flip it around that, okay, if there are sort of similar leakage radiation happening with a limited frequency range, we should be able to isolate that particular source as well.
Okay, thank you very much. One last quick question from Manos Zbokos. So he said, hello, lovely presentation. I was wondering, once SKA is built, would it be sensitive enough to push the limits as you mentioned?
Yeah. So SKA, very briefly, yes, I forgot to mention the SKA will allow us to go somewhere below 10 to the power 10, which is where we want to go. So it basically will allow us to go beyond the limit. And then depends on the number of, not for many stars, obviously, or at least for a few thousand stars, or at least for at least a million stars, we'll be able to reach up to that limit. So definitely it's going to be a new parameter space that we have not explored before with the SKA.
Cool. Very cool. Okay, I think we can thanks Vishal again once more time. Thank you very much. It was a very lovely presentation.
Thank you.
Thank you, Vishal.
Thank you very much.
Thank you so much. Thanks so much. And you have my email address, so please, if you have any questions.